Hello, and a very warm welcome to Sleepy Brain Science. What if I told you there are places in this universe so dark, so powerful, so utterly beyond imagination that even light itself cannot escape them? Tonight, we're going to drift gently into the mystery of black holes, 100 soft, fascinating facts that will carry you slowly into the deepest sleep. So close your eyes, take a long, slow breath, and let the universe hold you tonight. Let's begin. A black hole is a region in space where gravity is so strong that nothing at all, not even light, can escape from it. The idea of a black hole was first imagined in 1783 by an English scientist named John Michell, who called them dark stars. Albert Einstein's theory of general relativity, published in 1915, mathematically predicted that black holes could exist in our universe. The term black hole was not coined until 1967 by the physicist John Archibald Wheeler in a lecture at NASA. At the center of every black hole lies a singularity, a point of infinite density, where the known laws of physics simply stop working. The boundary around a black hole, beyond which nothing can return, is called the event horizon. It is a point of no return, calm and absolute. Black holes are not actually holes. They are incredibly dense objects containing enormous amounts of mass compressed into a very small space. If you could compress the entire Earth into a black hole, it would be roughly the size of a marble, just a tiny marble holding all that we know. Black holes come in different sizes. Stellar black holes form from collapsed stars. Supermassive ones hide quietly at the centers of most galaxies. There are also intermediate black holes and hypothetical primordial black holes that may have formed in the very first seconds after the Big Bang. Most stellar black holes form when a massive star, much larger than our own sun, runs out of fuel and collapses under its own weight in a dramatic explosion called a supernova. A star must be at least about 20 times more massive than our own sun for it to eventually collapse into a black hole. Our own sun will never become a black hole. It is simply not massive enough. Instead, it will quietly swell into a red giant billions of years from now. Black holes are invisible because they emit no light of their own. Scientists detect them by watching how they affect the stars and gas around them. Even though black holes are invisible, the space around them can glow brilliantly as superheated gas spirals inward and releases enormous amounts of energy. This glowing ring of gas and dust spiraling into a black hole is called an accretion disk. It can shine brighter than an entire galaxy of stars. Black holes are not cosmic vacuum cleaners. They do not randomly suck in objects from far away. Their gravity only dominates very close to them. If our sun were somehow replaced by a black hole of the same mass, Earth would simply continue orbiting it just as it does today. Only darkness would change.
The nearest known black hole to Earth is called Gaia BH1, located about 1,560 light-years away in the constellation of Ophiuchus, comfortingly distant. Scientists estimate there are around 100 million stellar mass black holes in our Milky Way galaxy alone, drifting silently through the dark. The supermassive black hole at the center of our Milky Way galaxy is called Sagittarius A star, and it has a mass equal to about 4 million suns. Despite being 4 million solar masses, Sagittarius A star is actually relatively calm and quiet for a galactic center black hole. The largest known black hole is TON 618, a quasar containing a black hole with a mass of 66 billion suns. It is almost incomprehensibly vast. Near a black hole, time slows down dramatically. This is called gravitational time dilation, predicted perfectly by Einstein's equations. If you hovered very close to a black hole's event horizon, time for you would pass much more slowly than someone watching from far away. This time dilation effect near black holes has inspired countless science fiction stories, including the film Interstellar, where 1 hour on a planet equals 7 years elsewhere. A process called spaghettification would occur if you fell feet first into a black hole. The difference in gravity between your head and feet would gently stretch you like a strand of cosmic pasta. Interestingly, for very large black holes, crossing the event horizon might feel like nothing at all. You wouldn't notice a difference until it was too late. Black holes can spin. A spinning black hole is called a Kerr black hole, named for physicist Roy Kerr, who described it mathematically in 1963. A spinning black hole drags space-time itself along with its rotation, a phenomenon called frame dragging, space itself gently swirling. Theoretical physicist Stephen Hawking proposed that black holes very slowly emit radiation, now called Hawking radiation. This means black holes can slowly evaporate over vast timescales. A black hole with the mass of our Sun would take about 10 to the power of 67 years to completely evaporate through Hawking radiation. That is unimaginably longer than the current age of the universe. The temperature of Hawking radiation from a stellar black hole is so incredibly cold, it is far colder than the cosmic microwave background radiation that fills all of space. Smaller black holes are actually hotter than larger ones in terms of Hawking radiation. This is one of physics's most beautiful and counterintuitive ideas. Black holes have electric charge. A charged, non-rotating black hole is described by the Reissner-Nordstrom solution, a quiet piece of mathematical elegance. A black hole has only 3 observable properties: mass, spin, and charge. Everything else about what fell into it is hidden forever. This is known as the no-hair theorem. Some physicists believe black holes may store information about everything that has fallen into them, encoded on their event horizon, like a cosmic hard drive. This idea that 3-dimensional information can be stored on a 2-dimensional surface is called the holographic principle. It suggests our entire universe may be a kind of hologram. Some theories suggest that the singularity inside a black hole may actually connect to another region of space-time through a tunnel called a wormhole or Einstein-Rosen bridge. Wormholes remain entirely theoretical. No evidence of one has ever been found, but the mathematics allows for their possibility, quietly waiting to be proven or disproven.
Around a black hole, the escape velocity exceeds the speed of light. This is why light itself is trapped. Nothing in the known universe travels faster than light. A photon sphere exists around a black hole at a distance of 1.5 times the Schwarzschild radius. Here, light travels in perfect circles, endlessly looping in the dark. The Schwarzschild radius defines the size of a black hole's event horizon. For an object to become a black hole, it must be compressed below this critical radius. For our Sun, the Schwarzschild radius is just under 3 kilometers, the entire mass of the Sun compressed into a sphere smaller than a city. For our Earth, the Schwarzschild radius is about 9 millimeters, our entire planet compressed to the size of a marble. Black holes can merge with each other. When two black holes spiral together and merge, they release enormous ripples in space-time called gravitational waves. Gravitational waves from two merging black holes were first detected on Earth on 14 September 2015 by the LIGO Observatory. It was a historic moment for all of science. These gravitational waves caused a distortion in spacetime smaller than 1/10,000th the width of a proton, yet scientists detected them perfectly. The two black holes that merged in 2015 were located 1.3 billion light-years away. Their collision happened when life on Earth was just single-celled organisms. We have now reached the halfway point of our journey tonight. Let your body feel heavy and warm. You are perfectly safe, and the universe is vast and beautiful around you. Let's continue. The first ever image of a black hole was captured in April 2019 by the Event Horizon Telescope, a global network of radio observatories working as one giant telescope. That first image showed the black hole at the center of galaxy M87, which is 6.5 billion times more massive than our Sun and 55 million light-years from Earth. The image looked like a glowing orange ring with a dark center. Scientists around the world described it as one of the most emotional moments in modern astronomy. In 2022, the Event Horizon Telescope released the first image of Sagittarius A star, the black hole at the center of our own Milky Way, a portrait of our galaxy's heart. Imaging Sagittarius A star was harder than M87 because it is smaller and its gas moves faster around it, making it flicker too quickly. Scientists needed special techniques to capture it. Quasars are among the brightest objects in the universe. They are powered by supermassive black holes devouring enormous amounts of gas at the centers of distant galaxies. Some quasars are so bright they outshine their entire host galaxy by a factor of hundreds. All of that light powered by matter spiraling silently into the dark. When material falls into a black hole, some of it can be launched back out as a powerful jet of energy, traveling at nearly the speed of light. These jets can extend for thousands of light years. The jets from a supermassive black hole can heat up and disrupt the gas in an entire galaxy, slowing down star formation for billions of years. Stars near the center of our galaxy orbit Sagittarius A star at extraordinary speeds. S2 completes one orbit every 16 years, moving at up to 3% of the speed of light. By carefully tracking S2 and other stars near our galactic center for decades, astronomers were able to confirm the existence of Sagittarius A star with great precision.
Andrea Ghez and Reinhard Genzel
won the Nobel Prize in Physics in 2020 for their work tracking stars around Sagittarius A star, confirming the black hole's presence. X-ray astronomy has revealed thousands of black holes by detecting the high-energy radiation emitted when they pull in nearby matter. Space telescopes like Chandra have been crucial to this. Binary star systems can contain a black hole paired with a normal star. The black hole slowly draws material from its partner, creating a glowing disk of stolen starlight. Cygnus X1 was one of the first strong black hole candidates identified in 1972. It is located about 6,000 light-years from Earth and contains a black hole 21 times the mass of our Sun. Stephen Hawking famously bet physicist Kip Thorne that Cygnus X1 was not a black hole. By 1990, Hawking conceded the bet, gracefully accepting the evidence. A tidal disruption event occurs when a star wanders too close to a black hole and is torn apart. For a brief moment, it flares brighter than 1 billion suns. Astronomers have observed hundreds of tidal disruption events, watching from safe distances as stars are quietly consumed by the cosmic dark. Some black holes grow extremely rapidly in the early universe, far faster than current models easily explain. These are called high redshift quasars, and they remain one of astronomy's great puzzles. The James Webb Space Telescope, launched in 2021, is now helping astronomers observe black holes forming in the very early universe, light from over 13 billion years ago. Webb has already detected supermassive black holes that existed when the universe was less than 1 billion years old, reshaping our understanding of how these giants form. Astronomers have discovered pairs of supermassive black holes slowly spiraling toward each other at the centers of merging galaxies. Their eventual collision will send gravitational waves across the cosmos. Pulsar timing arrays, networks of pulsating neutron stars used as precise cosmic clocks, may soon detect the low-frequency gravitational waves produced by these merging supermassive black holes. The information paradox is one of the deepest unsolved problems in physics. If black holes destroy information as they evaporate, that contradicts the laws of quantum mechanics. Some of the greatest minds in theoretical physics have debated the information paradox for decades, Hawking, Susskind, Penrose, and Maldacena among them. It remains beautifully unresolved. Juan Maldacena proposed in 1997 that black holes in certain universes might be equivalent to ordinary quantum systems on their boundary. This is called ADS-CFT correspondence, elegant beyond words. The entropy of a black hole, a measure of its disorder and hidden information, is proportional to the area of its event horizon, not its volume. This surprises physicists to this day. Black holes obey thermodynamic laws, just like a cup of tea cooling on your bedside table. The same beautiful mathematics that governs heat also governs the darkest objects in space. Jacob Bekenstein first proposed in 1972 that black holes have entropy and temperature. Hawking was initially skeptical, but later confirmed Bekenstein's insight with his own calculations.
Some cosmologists speculate that our entire universe might have been born inside a black hole in a parent universe, and that new universes might form inside black holes within ours. This idea, called the fecund universe hypothesis, was proposed by physicist Lee Smolin. Universes that create more black holes create more offspring universes, a kind of cosmic natural selection.
Black holes have inspired thousands of works of art, music, literature, and film. Humanity's imagination has always been drawn to the mystery of absolute darkness and infinite depth. The visual effects team for the film Interstellar worked with physicist Kip Thorne to simulate a black hole accurately. Their resulting image led to new scientific papers on gravitational lensing. Gravity near a black hole bends light so strongly that you could theoretically see the back of your own head if you stood just outside the event horizon. A phenomenon called gravitational lensing causes black holes to distort and magnify the light of objects behind them, creating halos and arcs of light around the invisible. Using gravitational lensing from black holes and other massive objects, astronomers can observe galaxies billions of light years away in incredible detail. The density of a supermassive black hole like M87's is actually quite low, lower than water in some cases. It is sheer size, not extreme compactness, that makes it a giant. Neutron stars are the densest objects we know of that are not black holes. A teaspoon of neutron star matter would weigh about 1 billion tons on Earth. When two neutron stars merge, they can form a black hole and simultaneously release a kilonova explosion, scattering gold and heavy elements across space. The gold in your jewelry may have been born this way. Black holes are not permanent. Given enough time, vastly beyond anything we can imagine, even the largest black holes will evaporate completely through Hawking radiation. Nothing is truly forever. In the extraordinarily far future, after all stars have burned out and all matter has decayed, the only things remaining in the universe may be black holes, drifting alone in total darkness. Eventually, even these last black holes will evaporate, leaving behind only a thin, cool radiation. The universe will reach a state of perfect, peaceful equilibrium, called the heat death. But that moment is so incomprehensibly far away, it need not concern us at all. Tonight, the universe is young and full of wonder, and you are safe and warm and resting. The atoms in your body were forged in the hearts of ancient stars, scattered through space by stellar explosions, and gathered slowly over billions of years into you. You are made of the same stuff as the universe itself. Black holes are not destroyers, they are transformers. Everything that falls into them becomes part of something new. Energy, radiation, ripples in space-time. Nothing is truly lost. When you look up at a dark sky, the light that reaches your eyes left its source thousands, millions, sometimes billions of years ago. You are always looking into the past. Somewhere in the universe right now, two black holes are slowly spiraling toward each other, pulling each other in over millions of years, in a slow, inevitable cosmic waltz. The universe is approximately 93 billion light-years across in what we can observe. Within it, black holes are forming, growing, merging, and fading in an endless, quiet cycle. You have now heard 99 facts about one of the most mysterious and wonderful things in all of existence. Your breathing is slow. Your body is at rest. You are exactly where you need to be. And the final fact, the most important one of all tonight, is simply this. You are a tiny, beautiful, extraordinary part of this vast and ancient universe. And tonight, in the quiet darkness, you are perfectly, peacefully at rest. That was our journey through 100 sleepy facts about black holes, right here on Sleepy Brain Science. If this video helped you drift off tonight, please leave a like before you go and subscribe to Sleepy Brain Science so you never miss a new video. Every week, we bring you new, calm, fascinating topics to help you relax and fall asleep peacefully. Sleep well, and we'll see you in the next one. Good night.